All right, so we're going to look at example 1. So example 1 is going to describe a scenario where we're going to apply that formula that we just looked at. So we're looking at this. So it says if a body is in air whose temperature is 20 degrees and the body cools from 50 to 40 in 30 minutes, how long is it going to take to cool to 30 degrees? So for starters, it just says a body. That doesn't necessarily mean like a body lying on the table there. It is just an item, okay? So whatever this thing is. But right now we know that its surrounding temperature is 20 degrees and the body itself is 50, cools from 50 to 40 in 30 minutes. So we want to know how long it's going to take to cool the next 10 degrees. I can tell you it's not going to be another 30 minutes because it doesn't decrease in a linear fashion. It's not a linear function. It's an exponential function. So it's going to slow down. It's going to cool down at a different rate. So that's what this question's about. So we're going to still need to find some information. Now, step 1 is to find C in our formula. So we know our formula is T equals CE to the KT plus S. Now, it feels like we already have the initial temperature, but it's not actually our initial C. And I'll get to that in a second. So let's look at our variables. We've got T, we've got little t, of course, capital T is temperature, little t is time, and we have capital S, and we got to figure out what C is. Those are all of our variables. K we're going to find out in a moment. To figure out this stuff, we have to consider the beginning because C is the beginning. So we're looking at this scenario at the beginning. Now it's tempting to say that our initial temperature is 50 degrees Celsius because if you look at it, it says it cools from 50 to 40. The difference though is in this situation, the temperature is not just made up the temperature of the actual item, but also the surrounding temperature. So we can use logic here and get the answer really, really quickly, but I want to show you mathematically why that answer works. So if we consider the fact that at the beginning it's 50 degrees, the actual body is 50 degrees Celsius, and the surrounding air is 20, so of that 50 degrees, 20 is taken care of from what the surrounding air is. That means the actual item must be 30. Okay, so the 50 gets split up into the 20 degrees comes from the surrounding temperature, and then the item itself, or the body itself, is 30. So I know that C is going to be 30. I'm going to show you mathematically why that is. So the temperature at the beginning is 50. That's what it says right there. The entire temperature. But the C is just the temperature of the item itself. The surrounding temperature we know is 20 from there. And then T, since we're talking the beginning, this is 0. Okay, 0 minutes in this case. So if we plug that in, we should get the C of 30 as well. And let's see what happens. So 50 equals something times e to the k times 0 plus 20. And you might think, well, how can I solve this if I don't have a k? But because I'm talking about the beginning, that k gets multiplied by 0. So that part doesn't matter. So that's e to the 0 plus 20. E to the 0, remember, is just some number to the power of 0. Any number to the power of 0 is 1. And so this formula, everything breaks down and we're just left with C is made, or 50 is made up of whatever the initial actual temperature plus the 20 surrounding. So then it's obvious that C is 30. And then that goes into this part of it. So even though we can use logic to say, hey, if it starts at 50, 20 is the outside temperature, that means the actual C value is 30. We know that math. I'd like us to see why that happens, and I'd like you to do these steps. Okay, so that's sort of an initial step, which is different than the questions that we did yesterday. But from here on, it's exactly the same. We just now have this extra variable. So step 2 is to find K. And this was the first thing we did yesterday. Find K. And we're going to do the same idea. To find the proportional constant, we have to take the snapshot of a scenario. So we can't do it at the beginning because k disappears. We got to find the snapshot of the scenario. We're still going to use the same formula, c times e to the kt plus s. But now we're going to get all of our variables at some snapshot. That's what we're trying to figure out. The c value we just figured out was 30. That doesn't change. That stays the same. It's always the initial value was always 30. And the s is going to stay the same. The surrounding temperature is always going to stay 20 in this case. But in the snapshot, we have new variables. And so now we'll go back and look at the question and figure out the snapshot that they tell us. So the snapshot says it started at 50, so that was the beginning, but it went to 40 in 30 minutes. There's our snapshot right there. So the scenario gets frozen in time, freeze, take the snapshot, we have information. We don't have the information at the end of the scenario, but we have the snapshot. So in the snapshot, we have a temperature of 40 degrees, and it happens at 30 minutes. All of this information will be used to find our k value. So now we can go off and plug it into the formula. 40 equals 30 e to the kt. So in this case, it is k times 30 minutes plus a surrounding of 20. And we're going to solve for k exactly how we did before, except we have this one extra step. We've got that 20 we got to get rid of, so I'm going to subtract 20 from both sides. So 40 minus 20 is 20. And this is 30k. This should just look like yesterday's note. Now I got to divide both sides by 30. I get 2/3. 20 over 30 is 2/3. E to the 30k. I'm going to leave it as 2/3. That'll be a little bit more accurate than changing it to the decimal 0.66666. Now to get at that, of course, I'm going to take the ln of both sides, just like I did yesterday. You've probably gotten used to maybe doing this in one step, because I know that since ln is an exponent or a logarithm, I can bring that 30k down. So you might go from this step to this step, I understand. And of course, we do that and realize that now we're taking the ln of e, and we know that the ln of e is 1. I wouldn't want to skip that step. That's an important part to remind us why this all works. Now we have 30k, so I just want to divide by 30. Divide by 30. And instead of saying divide by 30, I'm going to multiply by 1/30th, but it means the same thing. Okay, if you wanted to see that in 2 steps, it's actually divide by 30. I know that, but instead, I'm just going to write 1/30th ln 2/3. And again, you see why it's important to leave that as 2/3. This will be much more accurate. There's our k value. So just like yesterday, we used the snapshot to figure out the k value. We now know all the information we need, and we can go off and actually answer the question. So that's step 3. Use the same formula. T equals c e to the kt plus s. Put all my knowns over here and unknowns. Oh, not e. We don't need the e. We know what e is. K T and S. So K we just figured out was 1/30th of ln 2/3. C we figured out, and the top part of the question was 30. The question itself told us that S was 20. And then let's just go and remind ourselves what the question was. So the question says, how long will it take to get to 30 degrees? So how long is the time? So I must be trying to figure out the time to get a temperature of 30 degrees Celsius. And so now we can take all this information, plug it in. 30 equals 30 e to the 1/30th ln 2/3 times t plus 20. Subtract 20 from both sides. So I'm taking that and subtracting on the other side. So that's 10 equals 30 e to the 1/30th ln 2/3 t. I need the e by itself, so I'm going to divide both sides by 30. That'll give me 1/3 over here. E to the 1/30th ln 2/3 t. Again, I need access to that exponent so I can take the logarithm. Not any old logarithm, but the natural logarithm ln. So I'll take the ln of 1/3 and the ln of e to the 1/30th ln 2/3 t. Again, you might have brought down that exponent in that line. Totally get it. The ln e, as always, is just 1. What exponent you put on e to get e is 1. And now I need t by itself, so I got to divide by that whole thing. And I will get ln, ln 1/3 all over 1/30th ln 2/3 equals t. This is where your practice from last night's homework will be helpful, because we know it's a little tricky to put this in your calculator, and you can do it in a couple of steps, but be careful, and hopefully we've had the practice from yesterday to know that this actually works out to 81.3 minutes. So it takes 81.3 minutes to cool the next 10 degrees. And it's really fascinating. That's even more than I would have expected, because I said it took 30 minutes to cool the first 20 degrees, or sorry, first 10 degrees, but to cool the next 10 degrees, it takes 81 minutes before it gets to the next one. And that really goes and shows that idea that the hot water cools much faster than the cold water. And we're done.